Hello students, welcome to EPG Pathshala. Today we shall be discussing the applications of remote sensing and GIS in wasteland mapping. So far we all have studied what is remote sensing and what is GIS. So you all would be aware that remote sensing and GIS has various applications in the field of environmental sciences such as water quality monitoring, wetland mapping, land use, land cover changes, studying land degradation as well. So in this module we would be talking about wasteland mapping. We would be studying what is wasteland, what are the processes that lead to the generation of wastelands, how are the wastelands distributed in India, the methods for remote sensing and other methods that can be used for wastelands, as well as the inventory of wastelands in India. So at the end you would be able to understand what are the wastelands, how they are generated, how they can be reclaimed, and how remote sensing and GIS help us in this entire process. So the aim of this module is to understand the concept of wastelands and assess the role of remote sensing and GIS in wasteland mapping. At the end of this module, you would have obtained some idea about the wastelands, the factors leading to wasteland generation, as well as the reclamation of wastelands. You would also be able to understand as to how remote sensing and GIS would help in mapping of wastelands and the advantages of these techniques over conventional methods. So, coming to the first topic, what are wastelands? Wastelands are those lands which are presently not being used to their optimum potential due to some constraint such as location, environment, soil, financial and management constraints. The National Wasteland Development Board, Ministry of Environment, Forest and Climate Change, Government of India describes wasteland as degraded land which can be brought under vegetative cover with reasonable effort and which is currently underutilized, and land which is deteriorating for lack of appropriate water and soil management or on account of natural causes. With increasing human and animal pressure on land, the production of vegetation for food and other uses has extended to areas under great ecological stress and less favorable environment, leading to accelerated soil erosion and excessive land degradation. Vast stretches of land have thus been transformed into wasteland owing to desertification, soil salinity, waterlogging, excessive soil erosion and so on. So ecologically the value of wasteland is so precious that it cannot be measured by any monetary value. It's necessary to bring all the wastelands under productive and sustainable use through programs such as afforestation, pasture development, cropping pattern and other economic uses. This requires reliable database on the type, extent, location, morphogenesis, ownership of wastelands, and it's also necessary to categorize these wastelands in accordance with their intrinsic characteristics and causative factors. By reclaiming these wastelands, we can achieve the desired 1/3 of geographical area under forest, besides other advantages such as increasing biomass, climate and soil protection, economically and ecologically viable energy supply and biological diversity. It will also help in the creation of rural employment, strengthening of rural infrastructure and social development and equity. The process of waste generation is a complex one, and it is a complex ensemble of surface processes. Land degradation due to desertification, soil salinity, waterlogging, flooding, droughts, excessive soil erosion due to deforestation and unscientific agricultural practices have resulted in the creation of wastelands. So their management is essential both for continued agricultural productivity and protection of environment. This requires an inventory of these degraded lands to initiate appropriate reclamation and treatment plans. The information on the extent and spatial distribution of various kinds of wastelands is thus essential for strategic planning of development. Some possible reasons for the generation of the wastelands in the country are as follows. The first one is water erosion, which is the most widespread cause of land degradation and occurs widely in all agroclimatic zones. The displacement of soil material by water can result in either loss of topsoil or terrain deformation or both. This category includes processes such as splash erosion, sheet erosion, rill and gully erosion. The result is more loss of fertile topsoil and plant nutrients. In some cases where the subsoil has conchers and lime nodules, it gets exposed on the top, thereby altering the pH regime of the surface soil and subsequent nutrient holding capacity and their availability to plants. In wind erosion too, the surface soil is lost and gets deposited in other fertile areas, thereby altering the fertility and nutrient as well as water holding capacities. Next is wind erosion, which implies uniform displacement of topsoil by wind action. It can result in loss of topsoil and deposition of eroded material elsewhere, which leads to the formation of dunes. The uniform displacement of topsoil by wind action occurs in thin layers or sheets. The uneven displacement of soil material by wind action leads to deflation hollows and the dunes. The lifted medium to coarse soil particles may reduce the productivity of adjacent fertile land when they are deposited in the form of sand castings. The third one in this category is waterlogging, which is considered as a physical deterioration of land. It is affected by excessive ponding or logging of water for quite some period and affects the productivity of land or reduces the choice of taking crops. It occurs either because of topography, flooding or poor drainage conditions. The next one is salinization or alkalization. These problems generally occur in semi-arid and arid areas and could be both natural or man-made. It's a major problem resulting in the desiccation of plants due to high osmotic potential exerted on plants because of the presence of high concentration of salts. While salinization is mostly associated with the coastal areas and younger alluvial plains, alkalization happens mostly in inlands and older alluvial plains. It's generally alkalization is associated with waterlogging due to poor permeability of soil by the presence of sodium. Salinization can also result from improper management of canal irrigation water, resulting in the rise of water table. Next process is acidification. Any soil process or management practices which lead to the buildup of hydrogen cations in the soil will result in soil acidification. It also occurs when basic cations such as calcium, magnesium, potassium and sodium are lost from the soil, leading to high hydrogen ion concentration. It results in decrease of soil pH below 6.5 and generally occurs in region of very high rainfall. Increasing acidity through selective removal of calcium cations on the exchange complex affects the balance in nutrient availability. Glaciers are the areas under perpetual snow. Glacial processes degrade an area by two means. First is frost heaving and second is frost shattering. Frost heaving is defined as a process in glacial and periglacial environment where intense frost action and freezing of water evolves peculiar forms of rock, regolith and soil. The water crystallizes to ice below the surface horizon, leading to micro-relief variations on the surface. This process affects the germination and root growth of several crops, thereby limiting the productivity of land. Generally, these regions remain fallow during winters. Anthropogenic methods involve human economic activities such as mining, industrial activities that also contribute to decreased biological productivity, diversity and resilience of the land. Mining, brick kiln activities and industrial effluent affected areas are included under this type of degradation. Nutrient depletion or nutrient mining from fertile agricultural fields without replacement through manure or fertilizer results in nutrient deficiencies. Hence, the top fertile soil is almost permanently lost if not properly conserved. Chemical toxicity from industrial effluents and soil contaminated with poisonous chemicals affects the plant growth significantly. Other methods which are not included in the previous slides include mass movement, mass wastage, barren, rocky stony waste areas, riverine sand areas, sea ingression areas and so on. According to Food and Agriculture Organization of United Nations, various forms of land degradation such as soil erosion, chemical poisoning, salinization and loss through building or mining is about 5 to 7 megahectares from good cultivable lands. Coming to our third topic, distribution of wasteland in India. The problem of wasteland has become a serious issue in India, and it has increased with the development of technology for increasing the agricultural production. According to the Wasteland Atlas of India published in 2010, the wasteland area has now increased to 24% of the total geographical area. Although several agencies have estimated the total extent of wastelands, their figures as well as their definitions vary considerably. Reliable information on location, nature and extent of different wastelands on a large scale is essential for launching a program on wasteland development. Approximately 175 million hectares of land is degraded. The extent of land under agriculture is 143 million hectares, and again 56% of this suffers from varying degrees of degradation. This figure shows the values of wastelands to total geographical area in different states. As you can see, there is one state where the degradation is more than 50%, although it needs to be mentioned here that the state of Jammu and Kashmir has not been surveyed completely due to various areas being inaccessible. Two states have percentage between 40 to 50%, 5 between 20 to 40. One state has wasteland area greater than 15 to 20%, and subsequently we can see states with more than 10 to 15%, 5 to 10% and less than 5%. So nearly 53 million hectares are wasteland, and 22 million hectares of land have problems of salinity, alkalinity, soil erosion, waterlogging, shifting cultivation, or presently unused because of their undulating nature. The land area prone to floods has doubled from 20 megahectares to about 40 megahectares in the last 10 years. If these wastelands could be brought under cultivation or other uses like afforestation and horticulture, it can help in the socio-economic development of people and accelerate the overall economic growth. Awareness of this fact has resulted in the formation of National Wasteland Development Board under the auspices of National Land Use and Wasteland Development Council. The wasteland statistics indicated that about 63.85 million hectares of land, which account for 17% of the total geographical area, existed as wasteland in India, according to a report by National Remote Sensing Agency in 2007. Among all the states, Kerala has minimum percentage of 3.73 and Jammu and Kashmir has maximum of 64.55% of area under wasteland categories. So coming to our topic, like how remote sensing can help us in wasteland mapping. Among the new technologies that have emerged as an important tool for wasteland mapping are remote sensing and geographical information system. They help in detecting, assessing, mapping and monitoring these wastelands. The application of remotely sensed data in mapping degraded lands by spaceborne sensors started with the launch of first Earth Resources Technology satellite, popularly called as Landsat-1. Spaceborne multispectral data, by virtue of providing synoptic views of fairly large areas at regular intervals, have been found to be very effective in providing the necessary information on salt affected soils and waterlogged areas in a timely and cost effective manner. However, the satellites such as Landsat thematic mappers, SPOT and Indian remote sensing satellites with better spatial and spectral resolution have enabled us to map and monitor these degraded lands more efficiently. Information on geographical location, aerial extent and spatial distribution of wastelands is essential for their effective management and sustainable development. In the visual interpretation of satellite data, high soil moisture and surface waterlogged areas are identified as deep dark grey to light black in color, describing that areas that have high waterlogging risk. The dynamic nature of these wasteland categories warrants the use of multi-season satellite data for their accurate delineation. Hence, such images are needed to be georeferenced in a common coordinate and projection system. This remote sensing imagery is vital for the understanding of land cover change and thus forms an essential element of any effort to track land degradation and desertification trends. Change detection is the process of identifying differences in the state of an object or phenomena by observing it at different times. It's also an important process for monitoring and managing natural resources because it provides quantitative analysis of the spatial distribution of the population of interest. Further, GIS is also an effective tool in handling spatial data available at different scales. Voluminous point data such as soil information, rainfall, temperature, etc., and socioeconomic data to perform integrated analysis of data on various resources of any region and arrive at optimum solutions for various problems. To study the spatial dynamics of wastelands and to evaluate the utility of high resolution satellite data for wasteland mapping, the Indian remote sensing P6 satellite data with a resolution of 23.5 into 23.5 meter and topographical maps are generally used. The Planning Commission of India has recognized GIS as an invaluable planning tool in land use and wasteland development for identifying treatment areas and models, making trade-off calculations in choosing from competing land uses and carrying out simulations and impact assessments. The management of wastelands is a priority area in the context of national development. In 1991, the Ministry of Environment and Forest embarked upon an ambitious project to apply GIS technology for wasteland management. This was based on the prior work that was carried out in 1986 by the Department of Science under National Wasteland Identification Project that developed detailed wasteland maps of 147 districts in the country on a scale of 1:50,000. In this project, a task force was identified to evolve a suitable wasteland classification system. In this, 13 classes were identified that were approved by the Planning Commission, and it comprises of the following categories. These are gully and ravinous lands, uplands with or without scrub, waterlogged and marshy land, land affected by salinity, alkalinity that includes coastal or inland areas, shifting cultivation areas, sandy areas that may be desert area or a coastal area, mining or industrial wastelands, underutilized or degraded notified forest land, degraded pastures grazing land, degraded land under plantation crops, barren, rocky or stony waste or sheetrock areas, steep sloping areas and snow covered or glacial areas. So this figure shows the wasteland map of India that was prepared on a scale of 1:50,000 by National Remote Sensing Center under the Indian Space Research Organization. This map shows all the 13 classes with their subdivisions at various places in the country. These studies may be helpful for the planners and stakeholders in the process of overall sustainable development of the study area. For detection of temporal changes in the wasteland, two period temporal satellite data sets, that is corresponding to 2 time periods, are generally used. The methodology that is normally adopted for mapping at any scale consists of preparation of base map, online visual interpretation of satellite data, development of legend, ground truth collection, analysis of soil samples, classification of degradation classes, and finalization of maps in the light of field information and analytical data. The geodatabases generated using GIS and on-screen digitization techniques show the type, extent and spatial distribution of different wasteland categories present in the area. The image characteristics such as color, tone, texture, pattern, shape, size, location and association enable one to identify and delineate different types of wastelands. These delineations, however, are tentative and subject to confirmation in the field. Therefore, ground truth forms a vital input to mapping with remote sensing data. The key for interpretation is subject to change depending upon the season, scale and resolution of image. Certain categories of wasteland like salt affected land, waterlogged or marshy land and sandy areas can be easily delineated by virtue of their spectral separability, pattern and location, whereas gullied or ravagous land, shifting cultivation etc. can be delineated with moderate success. However, undulating upland with or without scrub cannot be easily delineated due to similar reflectance pattern with fallow land. The issue can however be resolved to some extent using multi-date images. In this figure showing the area-wise wasteland map of India on a scale of 1:50,000, 9 districts have an area greater than 5 lakh hectares, which chiefly belongs to the state of Gujarat, Rajasthan and Jammu and Kashmir. Coming to percentage wise wasteland map of India, 10 districts have area that is under wastelands for more than 50%. The next figure shows the data obtained for wasteland over the entire country for two periods, 2003 and 2006. This includes all the 13 categories of wasteland that have been defined by the National Wasteland Development Board. In the next figure, which shows the gullied and ravagous land obtained from satellite data, 228 districts have area that is less than 5%, while 8 districts have area above 5 to 10%. Wasteland areas that include land with or without scrub, 338 districts have area that is less than 5%, 127 districts between 5 to 10%, 39 districts between 10 to 15%, 18 between 15 to 20% and 16 districts have the wasteland area between 20 to 50%. In the wasteland map that shows out the waterlogged and marshy areas, 195 districts show wasteland that is less than 5%, 6 districts between 5 to 10% and 1 district between 10 to 15%. Wasteland map showing the lands that are affected with salinity and alkalinity. In this, 139 districts have wasteland area that is less than 5%, while 3 districts have area between 5 to 10%. Next map shows the wasteland map that represents the shifting cultivation area, where 44 districts have wasteland area less than 5%, 6 between 5 to 10%, 7 between 10 to 15, 4 between 15 to 20 and 3 between 20 to 50%. Wasteland map showing underutilized, degraded, notified or forest land includes 329 districts with wasteland area that is less than 5%, 72 districts between 5 to 10%, 30 districts between 10 to 15%, 10 districts between 15 to 20% and 5 districts between 20 to 50%. The next map shows 110 districts that have wasteland area less than 5% under degraded or pasture or grazing land and 1 district that has 10 to 15%. The next map shows 61 districts have less than 5% area under wasteland, whereas none of the states or districts have any higher percentage of area. The wasteland map that represents the sandy region such as desert, coastal or riverine areas show 163 districts that is less than 5%, 2 districts between 10 to 15, 1 between 15 to 20 and 1 between 20 to 50. In the last map that shows mining or industrial wastelands, about 128 districts show wastelands that is less than 5%. It is important to mention here that all these maps have been taken from the Wasteland Atlas of India that was published by the National Remote Sensing Center in 2010. Coming to the inventory of wastelands in India, using space-borne multispectral data, maps showing extent, spatial distribution and magnitude of eroded lands, salt affected soils, waterlogged areas, shifting cultivation at 1:250,000 and in 1:50,000 scales have been generated. The saline soils appear in different shades of white tone with fine to coarse texture on the false color composite prints of the satellite data owing to the presence of salts and are recognizable under normal crop growth. For assessing these soils, NRSC has prepared maps on 1:250,000 scale using satellite data from Landsat thematic mapper in association with other central and state government organizations and have thus prepared a digital atlas for India. This information is being used for planning land reclamation and soil conservation programs. In this atlas, each map shows village, forest compartment and micro watershed boundaries. In all the 532 districts out of 584 districts were covered by visual analysis of satellite data, and remaining 52 districts were mapped using digital analysis. Various categories of wastelands were identified and mapped based on image characteristics such as tone, color, texture, pattern, shape, size and association. Apart from the wasteland categories, transport network, habitation and village boundaries were shown on the final map so that the planners can easily locate various wastelands on the ground at the time of formulation and execution of various projects related to management and reclamation of wasteland. In this, the following 13 categories of wastelands have been identified and mapped on 1:50,000 scale using remote sensing technology. This table shows the percentage of total area covered under wasteland, and you can see that out of all the 13 classes, the wasteland with or without scrub occupies the highest percentage of 6.13%, followed by underutilized or degraded notified forest land, that is 4.44%, and next one is barren, rocky or stony waste or sheetrock area that occupies 2.04%. The least area under this category is occupied by mining or industrial wastelands. So coming to these categories of wasteland, barren lands are those ecosystems in which less than 1/3 of the area has vegetation cover. In general, barren land has thin soil, sand or rocks. It's unsuitable for agriculture due to both climatic and terrain factors. Such lands are deteriorating and need soil management. Next one is salt affected area, which is generally characterized as the land that has an adverse effect on most of the plants. They are found in river plains and associated with irrigated lands. The salt affected land is generally characterized as the land that has adverse effect on the growth of plants due to excessive presence of soluble or high exchangeable sodium. Gullied lands are narrow and deep channels developed as a result of wearing away of soil by running water. They develop from the rills, which are tiny channels a few centimeters deep, formed by the impact of rainfall and wearing action of runoff generated. Sandy areas are covered with relatively large particles and occur in the form of sand dunes, beaches, sands and wind-blown dunes. Stony waste are rock exposure that are often barren and devoid of soil cover and vegetation and not suitable for cultivation. It also does not support groundwater recharge and habitat for ground flora and fauna. Land with or without scrub is a landscape that is characterized by the presence of thorny scrub and herb species. They are seen along the ridges and valley complex and steep slope areas. Most of these areas are associated with poor vegetal cover. Land under this class is generally prone to degradation and may not have scrub cover and is confined to uplands generally. So coming to our final topic of wasteland reclamation. So far you have understood that there is a need to reverse this trend of wasteland generation and restore the wastelands to their production potential in order to meet the demands of increasing population and other development activities. Remote sensing also forms a critical element in early warning systems for drought and famine. Many national reports to United Nations Convention to combat desertification now feature estimates of land degradation based on remote sensing data. Planning for development of degraded lands, including erosion affected and waterlogged soils, calls for up-to-date information on their geographical location, areal extent and spatial distribution. Conventionally, the information on different categories of wasteland is arrived at by compilation from village records, which was primarily statistical in nature. So in this table you can see the various reclamation methods for wasteland types. For gullied and ravinous lands, leveling of gullies can be done or construction of check dams can be carried out. For uplands with or without scrub, contour bunding, trenching and terracing can be carried out. For degraded, underutilized forest land, grazing activity needs to be regulated, as well as illegal forest felling of trees needs to be restricted. For stony wastelands, regulating the grazing activity is important, and for wetlands, passage to the log water needs to be provided to reduce the waterlogging. So, coming to the end of our chapters, in recent years there has been an increased concern among planners in the country on the types of wastelands and their precise spatial distribution and timely availability of the information. With the advent of remote sensing, a major technological breakthrough has happened in the method of acquiring information about natural resources. Land degradation study requires an accurate assessment of how widespread it is, how severe the damage is, and whether or not it is practically controllable or reversible. The data derived from the satellite and topographic studies have brought out the factor that wasteland should be managed properly. The potentiality of satellite images for the preparation of accurate baseline information is well acknowledged. The remote sensing and GIS technology is one of the master tools in managing these wastelands of the country, starting from mapping, characterization, possible reasons, protection and reclamation of wasteland. At each step of management, remote sensing and GIS has proven to be economically sound, speedy and accurate method. Generation of human resource and skilled personnel having proper training on remote sensing and GIS can contribute a lot in the entire process of wasteland management. So dear students, at the end of this module, I hope you would be able to understand how the wastelands are generated, what are wastelands and how they are distributed in our country. You would also be able to appreciate how remote sensing and GIS help us in mapping the wastelands and how they are more advantageous over the conventional methods by providing us synoptic views of and repeatability over large areas, which is not possible by field studies as such. Thank you.